Hi students, today we are going to derive the general solution of any quadratic equation, the solution which had been derived way back by Brahmagupta in 600 AD and then the complete solution mentioned by Sridhara in the 9th century. So it's not that quadratic equations were not being solved before that. It was being solved as long back as 2000 BC by Babylonians, and the problem set was a very simple kind of problem set. Like, you have the area of a rectangle given to you as say 10, and say the semi perimeter is given to you as 7. Then what would be the sides? So you'll make up an equation. You'll say that the area of a rectangle is a into b, where a and b are the sides, and the semi perimeter will be a plus b, and then you have got two equations and two variables to solve. When you try to solve this, you'll be ending up in an equation which is called quadratic equation. So we already know what is a quadratic equation, but a very quick recap. So before going on to the quadratic equation, we'll just recap what is a quadratic polynomial. A quadratic polynomial is a polynomial with the highest degree of 2. So if I write a general one, it will be ax square plus bx plus c. That's a polynomial. That's a quadratic polynomial. And I'm just referring it back because we'll be doing a bunch of graph where this px, I'll be calling it as y, and we'll graph the output value. When we put some values of x, we are calling them as input values, and then the resultant value, which is your px, we'll be plotting it in the xy plane with the px being the y value. So the output will be the y value, and when we plot it, we get a parabolic graph. So that's your quadratic polynomial, which you have already done. The graphing is also done in the previous chapter. Now, what is quadratic equation? This expression, this polynomial expression, when you equate it to a number, and particularly 0, if you're not equating it to 0, if you are equating it to some other number, then you can take it on the other side and make the other side as 0 and write ax square plus bx plus c, the quadratic expression or the polynomial equated it to 0 is your quadratic equation. Now, what's the difference between the two? There's a big difference between the two. This one is serving as a pair of values. For a certain x, you'll have a certain y. If you have x as 1, you'll have a certain y. You have x as minus 100, you'll have a certain y. You have a lot of y's with a lot of x's inputted. Now, in this one, this is particularly talking about that value of x where this expression will become 0. So in fact, the root of this quadratic equation, when you solve this, you'll get the root. The root of this quadratic equation will be same as the 0 of this polynomial. What is the 0 of the polynomial? Which value of x makes the polynomial px as 0? So 0 of the polynomial will be same as the root of the quadratic equation, but we don't say 0 of the quadratic equation, we don't say root of the polynomial. So mind you, they may lead to the same values, but they mean two different things. So I'll emphasize between the difference between a polynomial and the quadratic equation while I'm graphing, and then in the other section of this chapter, obviously I'll be talking in detail about that, but this section is about deriving the general formula. Till now, what you have been doing is you have been factorizing the polynomial, you have been factorizing the quadratic polynomial, and you equate it to 0, means the factors must be equal to 0, meaning to say this polynomial over here, px, if I'm able to factorize, I'm not writing a particular polynomial, I'm just writing a general one. It would look like a x minus certain value, which is called one of the zeros, and x minus beta, x minus alpha into x minus beta. These are the two factors apart from a you have taken common. So we know that when we put x equal to alpha, this part is going to become 0, x minus alpha is going to become 0, and the whole polynomial will become 0. So that will result in a polynomial value when x is equal to alpha. So we'll write it as p of alpha will become 0. Similarly, when you put x is equal to beta, you'll get the polynomial value again as 0, meaning to say alpha and beta were the two zeros of this polynomial, So this is how we have been doing so far, factorizing a certain quadratic polynomial into two linear factors and equating it to 0, which might not be possible in all the cases. In fact, in most of the cases, if a real life in a real life situation, you encounter a quadratic equation, or you're solving a certain question and you encounter a quadratic equation, then more often than not, you won't be able to factorize. You won't be able to factorize. Now this situation, let me try to solve this. And here, again, I think I've given you pretty numbers so that you can factorize. This is what has been happening all the time with the questions what you have encountered till now. When I'm trying to solve this, let me just substitute the b value in terms of a over here. So b is 10 by a, and I'll put it in the equation number 2. What I get is a plus, instead of b, I'll write 10 by a is equal to 7. Now if I cross multiply, or if I multiply a all over, I get a square plus 10 is equal to 7a. If I take everything on one side, it is a square minus 7a plus 10 equal to 0. That's your quadratic equation. So this was a real life problem which they were trying to solve, and they were able to solve it if it was giving you positive numbers as the solution, if it was giving you rational numbers as the solution. But if the numbers went as negative, then negative numbers were not thought to be real solution those days, and they were discarded. Irrational numbers were not the solutions, and rightly so, because they were never dealing with those numbers. They were dealing with numbers which was physically possible. So because they were using this maths to do actual trade and other stuff. Now if I try to solve it by factorizing, then I'll split the middle term, and what do I get? Will I be able to split it? Luckily I'm able to split it in this case. Minus 5a minus 2a plus 10 is equal to 0. A common, a minus 5 minus 2 common, a minus 5 is equal to 0. Among the two, a minus 5 common and a minus 2 is equal to 0. Don't worry about this part. This is not the concern of this lesson. What I'm doing over here is just recapping what we have already done before. So this part I'm not teaching, and what we get is, we get a is either equal to 5 or a is equal to 2. Now if a is equal to 5, I'll put it in any one of the equation. I'll get my b is equal to 2. So when a is equal to 5, my b will be equal to 2, and when my a is equal to 2, my b is equal to 5. So this 5 and 2 were the pair of the answer. So they had given that the area is 10, semi-perimeter is 7. What would be the sides? The sides would be 5 and 2. So this kind of solution they were able to make. But suppose you are not able to split the middle term such that you get the common factors a minus 5 and a minus 5, and you are able to factorize like this in a pretty way. Suppose that doesn't happen, which is the more probable chance of not happening in a real life situation. If I tell you the area was 12 and the semi-perimeter was 7, and go do again, you won't be able to do. So how to do? Does that have a solution? Do we have a certain rectangle where instead of 10, the area is 12 and a plus b is equal to 7? Yes, it is very much possible. Are those a and b pretty numbers like this, 2 and 5? No, they are not. So now, since we are in higher standard, we don't have to deal with only pretty numbers. So if we are not able to factorize, there is another sure shot method of doing it, where even the ones which you are able to factorize, you can find those, and the ones you can't factorize, those answers also you can get. So before I go on to mathematically solve those questions, we'll just quickly look into the graphs of these polynomials and understand that what we are trying to do. So again, it is just for your understanding. It would be great if you understand the graphs well, because it is going to help you later on in later years, and the relevance of this chapter will become even more. So you can go very slow with it. You can see what is happening. You can try to plot yourself also in your notebooks. So let's understand the graph well before we go on for the general solution of quadratic equation, the mathematical derivation. So let's analyze the graph of our simplest quadratic polynomial, y is equal to x square. And how did we get this beautiful parabola? So we inputted some values of x is equal to 1, x is equal to 2, x is equal to minus 1. And when we put those values, let's say x is equal to 2, then what do we get y as? We get y as 4. And when we put x is equal to minus 2, we get 4 again. X is equal to minus 1, we get y is equal to 1. And then when we connect them, then we get a curve, not a straight line. So that's your beautiful parabola, a quadratic polynomial graph. And I guess we have done this earlier also. Now any quadratic polynomial with a coefficient of x square as 1. say y is equal to x square minus 4x plus 3 or whatever, a quadratic polynomial with a x square coefficient as 1 would be this ditto same graph shifted left, right, up or down. It would be the same contour, same curve, the same graph which is shifted. Very surprising. And we would see why. Watch this green graph. It's the x square graph, y is equal to x square graph, and I'm taking it up. I'm taking it vertically up. And if it lands here, it is y is equal to x square plus 2 now. It's a different polynomial, y is equal to x square plus 2, but it's the same x square graph which has been lifted up. And if I make it go down, it is y is equal to x square minus 1 here, and y is equal to x square minus 2 over here. And you shift it to the right, then this becomes y is equal to x minus 1 the whole square, and over here it becomes y is equal to x minus 2 the whole square, which is y is equal to x square minus 4x plus 4. It's touching the x-axis at 2 and cutting the y-axis at 4. So let me write down the polynomial for this graph, which is y is equal to x square minus 4x plus 4, and do a bit of investigation. Now if I write it in the factorized form, which is x minus 2 into x minus 2 the whole square, then it would be easier for me to figure out when would this polynomial, when would the y value become 0. It would become 0 when x is equal to 2. So 2 is called the 0 of the polynomial. When you put the x value as 2, the polynomial becomes 0. 2 is called the 0 of the polynomial. And when I'm talking about root, I have to write the quadratic equation, which is x square minus 4x plus 4 is equal to 0. So if I solve this and find out the value of x, which is satisfying the equation, then it's called the root of the quadratic equation. So again, to solve it, I would rather write in the factorized form x minus 2 the whole square is equal to 0. And what I get is x minus 2 is equal to 0, which is x is equal to 2. So that's the root of this quadratic equation. And this quadratic equation x square minus 4x plus 4 is equal to 0 was an equation in single variable, that's x alone. I'm not talking about the polynomial, just this quadratic equation x square minus 4x plus 4 is equal to 0. And on solving this equation, which was in a single variable, I get the answer as x is equal to 2. So I can say x is equal to 2 is a solution to this quadratic equation. These are just the terminologies, and I thought we should be just clear with them. What is a 0? What's a root? What's a solution? So to clarify on this part, we see that various inputs of x gives you various outputs in y, that's the polynomial. So polynomial can have various values depending on the input value, which is in fact creating the graph. So this graph is not for the equation, this graph is for the polynomial. And that input of x, which makes the output value as 0, which makes the y value is 0, that x is called the 0 of the polynomial. And in a quadratic equation, there are no outputs. There are not various values of x which can be put. There are just two values of x which can satisfy the equation. So those two values of x are called the roots. So we had written the LHS of the quadratic equation in the factorized form, which is x minus 2 the whole square is equal to 0, and which translates to x minus 2 is equal to 0, which is the solution, or x is equal to 2, which is the root of this quadratic equation. Now let me move this green graph down a bit, and let me do it precisely so that it is cutting the x-axis at 1 and 3, and you can see that it's cutting the y-axis at 3. Now let me write the polynomial which represents this new graph. It is y is equal to x square minus 4x, and then what would you say? It is a plus 3 this time instead of a plus 4, because I've dropped it down by 1. So instead of 4, I've written plus 3. And if you don't believe me, you may cross check by plotting it by putting various values of x and seeing the y value is matching or not. Like when you put x is equal to 1, you can see that the y becomes 0 or not. So when you put x is equal to 1, you do get y is equal to 0. And again, when you put x is equal to 3, you get y is equal to 0 again, which you can take a moment and see in the graph. You can also see that when x is equal to 0, y is equal to 3. That is where it is cutting the y-axis. So had the graph not been plotted for us and it was asked that where is this polynomial going to become 0, where is the graph going to cut the x-axis, then again we would have gone for factorizing it. and we'll try our luck by splitting the middle term. So it becomes x square minus x minus 3x plus 3. So which in the factor form is x minus 1 into x minus 3. I'm skipping a step over here. Now it is quite easy to see when will y be 0. It would be 0 when x is equal to 1 or x is equal to 3. So these are the two zeros of the polynomial, 1 and 3. Now instead of working on the polynomial given, suppose we had this as a quadratic equation, that is x square minus 4x plus 3 is equal to 0. Now this is a quadratic equation, and it is not going to create this parabolic graph, but it is something what we can solve. It is an equation in a single variable, and we again do the same factorization, and what we get is the solution of this is either x is equal to 1 or x is equal to 3. So those are the roots of this quadratic equation. Now for this quadratic equation, we were quite lucky to be able to factorize it by splitting the middle term. Let us see if I had dropped the green graph not by 1 but by 2, and it looks something like this, then the polynomial would be y is equal to x square minus 4x plus 2. Again, you can see that the graph is cutting the x-axis at two places. That means there are two values of x where the y is becoming 0. And how to get those values? Again, we need to factorize it and get the two factors, the two linear factors, so that we can get the two values. But this time around, the factors won't be pretty numbers as the previous one, and we might not get factors which are rational. So if the factors are irrational, it would be impossible for us to split the middle term and get those factors. So in fact, for this graph, the x values for which y is becoming 0 are irrational numbers, and hence that's the problem at hand. If we have a quadratic equation x square minus 4x plus 2 equal to 0, then how to solve it and get the roots? So we know there are two values of x which makes this expression 0, one between somewhere between 0 and 1, and one somewhere beyond 3. So is the value of x which makes it 0 0 0.5? Is x equal to 0 0.5? Let's just put in and see. So if I put x equal to 0 0.5, I get x square as 0 0.25 minus 4x as minus 2 plus 2, and is that equal to 0? So y came pretty near to 0, but it wasn't 0. And we can't be doing a hit and trial like this, hunting for x which makes our y 0. In fact, we won't be able to do it by hit and trial. And we need to have a mathematical precise way of hunting for that x or finding or solving for that x. And that would be the method of solving any quadratic equation, whether x is rational or irrational. So the question is, how do we solve these quadratic equation? We know that the associate quadratic polynomial is cutting the x-axis in these two places. On the x-axis, which is a real number line, and the real number consists of both irrational and rational numbers. And mind you, if the solution was a rational number, if x was a rational number, you would be able to split the middle term no matter what. So I'll repeat, a split of the middle term is possible when the solution is a rational number. When it is irrational number, then you won't be able to split the middle term and get the answer. And by the way, if I cut the real number line at any point, any random point, the probability of that point being a rational number is quite low. It would be, say, something like if I ask you choose a number between 0 and 1000, and what's the probability that the square root of that number is a rational number? That's quite low. Meaning to say, if we have a real life quadratic equation to solve, a natural quadratic equation to solve, it would be very improbable that we would be able to split the middle term and factorize the quadratic equation and get it. So you might be a bit surprised because you had been solving the quadratic equation by splitting the middle term till now. But the fact is, those questions were made in such a way such that you are able to split the middle term and solve it. It's like if I ask you what's the square root of 36, and then I ask you to do the square root of 49, and don't dare to ask any number in between like 37, 38, 39, what's the square root of those. So it is that much improbable for a natural quadratic equation to be able to be split at the middle term. Now, before forming a method of solving the quadratic equation, let me just take the green polynomial, the green graph, up instead of down. So let me take it up by 1 and write a relevant quadratic polynomial expression for it. So instead of being plus 4, it's a plus 5 now. So what's the 0 for this polynomial? What's the solution for, or the root for the quadratic equation x square minus 4x plus 5 is equal to 0? So what do you think? What is the solution for this quadratic equation? Yeah, it won't have any solution. I won't even give it a try. Why? Because we are looking at the graph and we see that no value of x is making that y 0. So this quadratic equation would never be 0. At the minimum, the y value is equal to 1 when your x is equal to 2 over here. So when you put x is equal to 2, you are going to get y is equal to 1. You can check out in the expression. If you take any other value of x more than 2 or less than 2, say 3 and 1, your y value is going to be more than 1 in both the cases. So you can in fact try out and we'll see the symmetry also. We have taken x 1 away from 2 on either side and we assume that y will be greater than 1 in both cases. So when x is equal to 1, x square minus 4x plus 5 is going to give you y is equal to 2. So when x is equal to 1, we are getting y is equal to 2. When we write x is equal to, when we try x is equal to 3, again we get y is equal to 2. You can check out 3 square minus 4 into 3 plus 5 is going to give you 9 minus 12 plus 5, which is 2 again. So when x is equal to 1 or 3, y is equal to 2. That's here. I'm just marking it over here. When x is equal to 1 or 3, in both cases y is equal to 2. So if this quadratic equation was given and asked for the roots, then we don't have any real roots, no real roots. And had the graph not been given to us, we would have to have some method to find out that it was not having any real roots. Plotting the polynomial is one method, but uh, we would go for a more precise mathematical solution. Just to summarize, when the graph was just touching the x-axis, the number of zeros for the polynomial was 1. It was having just 1 0. X minus 2 the whole square. When that was a polynomial, your x was equal to 2, just 1 0. When the graph was dropped down, it was cutting in two places, then it has two zeros. And when the graph is lifted up, it is not having any zero. So let me just slide the x square curve towards the left this time and drop it down by 2. So that's your new curve, and let it be in orange. So the associated polynomial for this curve is y is equal to x square plus 4x plus 2, and we need to find the zeros for this. In fact, we are doing quadratic equations, so the quadratic equation x square plus 4x plus 2 equal to 0 is the problem at hand and need to be solved. Now you can keep breaking your head, but solving it by splitting the middle term would be a real pain. Before going on to formulate the method for solving any quadratic equation, allow me please to touch upon a very interesting concept over here. Let me ask you one thing. If I say I'm solving for half times x square plus 4x plus 2 equal to 0, will the solution for this pink equation be different from this orange equation? Obviously not. Whatever value of x is going to make this orange expression 0 is going to make this pink expression also as 0. And by all means of math, the quadratic equation, the orange one and the pink one, are identical. Both are same quadratic equations. But if I talk about the quadratic polynomial y is equal to half x in the bracket x square plus 4x plus 2, or if I open the bracket, it's equal to x square by 2 plus 2x plus 1. Is this polynomial same as that polynomial? Is the pink one same as orange? No, they are not. If I'm going to plot it out, would I get the same plot? No, I won't. I will get this pink plot. But can you see that in this pink plot also, my y value is 0 at the same values of x. The whole of the plotting, the whole of the graph is different except when y is equal to 0. The quadratic equation is same. The equation is talking about the polynomial being 0, the height being 0. So I hope you got the point that two different quadratic polynomials can bear the same quadratic equation. I'd put a factor of half in the first quadratic polynomial, and the polynomial had gone flatter. So if I multiply the quadratic equation x square plus 4x plus 2 equal to 0, I'm not writing the equal to 0 right now, with say 3 by 2 on both sides. So I'll just put equal to 0 on the other side. The solution for this green quadratic equation would be same as what it was for the pink one or the orange one, because after all the same value of x is going to make the green one also equal to 0. But if I talk about the polynomial y is equal to 3 by 2 x square, I'll just open up the bracket and write 3 by 2 x square plus 6x plus 3, then this polynomial is a completely different one, except that it is cutting the x-axis at the same spot where the orange one or the pink one was. So if I plot this green polynomial, then it would look like this green graph. And you can see that except for where it is cutting the x-axis, the rest of the whole plot is quite different from the other two. Now let us go to the problem at hand, that is forming a method of solving any quadratic equation.